We are now going to go through a few different shapes and examine what the fields are going to look like from them. Now, we're not going to do the full approach of doing each of these since that would take quite a bit of time, but it's the same process that we saw for the line. So I'll sketch some aspects of this for each of them. What we're going to start with is a ring, and the ring is an interesting choice because this really is just a line of charge, but instead of being straight, it is bent in a circle. Now, because of that, we need to actually work inherently in 3 dimensions here. So you can see you have y, x, and then z. Now, obviously, the book hires professional artists who can draw 3-dimensional things like this. I don't expect you to be able to do quite so well. I know I can't. So anytime you need to draw a 3-dimensional geometry, feel free to show one view that, for instance, is y and x, which would be showing the ring itself, and then another one, which for instance is maybe y and z, showing how the point that we're calculating here relates to the ring, which you're then seeing edge on. So feel free to do 2 representations in the coordinate system if you don't think you can do 3 dimensions well. So the next thing is that here we're inherently only breaking our ring which has total charge Q, and we know that it has radius R. So R, capital R, is describing the ring. Z is then the distance from the center of the ring to our point. Now, this calculation we would do is only on the axis of the ring. So starting from the center and going perpendicular from the plane of the ring. So it's important to understand what we mean when we talk about axis, right? Because you might think about the axis of this being the y direction or the x direction, but it's not. When we say x-axis, we mean the axis of the ring as this perpendicular direction. So be ready to be asked questions where it's a question asking you about the axis of something or a point on the axis from a disk, and you need to know what that means. This is in a way terminology that has specific meaning. So we're going to be looking at this point. So if you think about it, looking at just one point here and one point here is really similar to when we looked at the rod. We see that the components of the electric field vectors that are up and down or in the y direction here are going to cancel. So it's really just the direction that they share, which now is the z direction, which adds up. So again, there's a symmetry argument to be made here. So the setup, the first few steps for the ring of charge looks just like the line of charge, but the difference is what we would be integrating over. But what's clever about the ring of charge is if you look, every single place on the ring, like we can take these 2 points, they are actually the same distance, right? Remember, Ri describes the location of each of these points, but each point is actually the same distance from this. So that means that we don't really have to actually do an integral here, that every single little delta Q has the same Ri and the same angle. So you would still want to set it up in this very careful geometric way. And remember that this Z isn't just your coordinate, it is again that distance. But then you see that you don't actually have to do an integral. It's that your entire charge Q, where I mean Q, capital Q, not just delta Q, has this radius and that theta. So that's really helpful. This situation in particular simplifies down and you don't have to do the integral. I struggle to think about many other situations where that's going to be the case, and had you actually set it up to do the integral, it still really would have been fine. So make sure that, again, you're thinking about that setup carefully to take your delta Q, look at the radius, look at the angle, and then remember that you're really only looking at components. And here, again, no need to do the integral. This is the answer we get in the end. And note that it has some similarities to the line of charge, but it obviously is also different. And in this case, we haven't defined it in terms of linear charge. You just see the total charge up here, but this could have been defined in terms of linear charge. And in this case, the linear charge would be thought of a little bit differently. because the ring is defined to have a radius, and so the length of the line, right, the entire length that it's around is the circumference, 2 pi r. So that's how we could rewrite this in terms of the charge density, linear charge density. So it's interesting to think about what's happening with this form, that we have a z squared plus r squared on the bottom to the 3/2 power, but we also have a z on the top. That actually gives this a fairly complicated functional form. And the field is actually 0 exactly at the center. And being at the center, right, note that this is z, would be 0 here. So we don't get that it's undefined, because on the bottom you don't have z, you have z plus something. We have 0 divided by a value that's 0. And so if you think about it though, if you're in the exact center of the ring, there's no z component from each of these pieces. Each of these pieces is actually creating an electric field, but it is exactly canceled by one on the other side of the ring, and there's no shared z coordinate, a z component. So the field at the exact center is 0, and then it rises, and then it falls. So there's actually a maximum at some distance here. And you can think about that as a little bit, again, in terms of components, that as you change different distances away, that angle theta, which now actually does go to the entire ring, changes. And remember that we know the electric field we have in total is just the z component. But the electric field from each of these pieces actually is larger, and we're only taking a component of it. So if we're really close to the ring, theta is very large, and our electric field is largely not in the z direction. As we're really far away, we're just, in that case, really far away from our ring. And in that case, the electric field is much smaller. So there's actually a maximal distance here. The other thing that's a little bit interesting is to ask, well, does this look like a point charge if we're really far away? And the answer is yes. What we can do is say that if we're really far away, we don't worry about r, that would effectively go to 0, and we're left with z squared to the 3/2 power. That would be z cubed on the bottom, which leaves us with z to the squared if we cancel the one on the top. So if we're really far away from a ring of charge, it once again simplifies down to the point charge, the electric field from a point charge. Again, that isn't what it looks like at all if you're really close, but that is what it looks like if you're really far away.